In this video, I wanted to talk about physically implementing ODE45 in MATLAB. We've done a lot of talk in the previous videos motivating ODE45 and trying to establish a foundation for using it. But in this video, we'll talk about how to physically implement it in MATLAB and how to write code that will run ODE45. If you haven't done so already, I would really recommend reading the ODE45 documentation on MathWorks' website. A point of note between these videos and that documentation: the MathWorks documentation represents the state variable vector as the variable y. And here I've done it with this script s that I introduced in our last video. That's the main difference between the two. I've found that students often get confused with the state variable vector being y and having perhaps a state variable as y as well. And so this is designed somewhat to avoid some of that confusion. So let's talk about these inputs and outputs of ODE45. This first input, the at function, is going to be a function handle that points MATLAB towards a function that describes how to get from a state variable vector s to s dot. If you remember back to our discussions about Euler's method, MATLAB can perform a numerical integration if it can get from a state variable vector at any time t to the derivative of that at the same time step t. So this function here will describe how this derivative is taken. Tspan is going to be a row vector that tells MATLAB when to start integration and when to end it. So a t-start and a t-final. So these are just time in seconds in which to start and end the integration. And this s0 here represents the initial condition of our state variable vector. So it represents our state variables, and if you remember back to our previous example that we'll elaborate more on here in this video as we go on, we had state variables of x and x dot. So this state variable vector not represents these at t start. Now I say at t start and not at time 0 is that you could have your starting time be 1 or 2 seconds rather than 0, and this initial vector will always correspond to that initial time. As far as the outputs go for ODE45, we have two outputs that come out. We have t out, which is going to be a vector of time points, represented as, I'm going to write them here as t1, t2, t3, and so on and so forth. And t1 would represent or correspond with t start. So these should be the same number. The second output here, s out, represents our state variable vector at each time point. So if we consider x and x dot as our state variables, this would be x at t1 and x dot at t1. This would be x at t2 in the second row and x dot at t2 in the second row. And you'd have x at t3, x dot at t3, so on and so forth. So this is a matrix that is the same length as t out, and each row corresponds to a different time step, where each column corresponds to a different state variable. And the order of those columns is the same order as our state variable vector. So you'd have x and x dot. So this first column is all x, second column is all x dot. So one thing that we haven't talked much about is this function. So in order to tell MATLAB how to take a derivative, we need to set up a function to point it to. And this function has a particular format to it. So in MATLAB, if we wanted to set up this function, it would look something like function where the output is s dot. So I'm going to represent this as s dot. The function name, which I'm just going to call fun for now, and it needs to have two inputs. That first input needs to be time t, and the second input is going to be your state variable vector. And within the function, you'll describe how to get from the state variable vector s to s dot. And this will become a bit more clear as we start coding this up. So this is the components that you need to make MATLAB function. I said this earlier in our previous video, but the main components are we need initial conditions and we need a means of telling MATLAB how to get from s to s dot. The time span just tells us over which time frame to conduct that integration. So scrolling down, I've just copy and pasted the example problem that we went through last time. Just to refresh your memory, we have a mass on a spring that has a resting length of xr. And doing our Newton's equation, we came up with the second order differential equation minus k over m times x minus xr. We decided that our state variables should be x and x dot, which allowed us to represent this second order differential equation as a series of first order differential equations. This series of first order differential equations is exactly what we want to plug into our function. So this is our ODE function that ODE45 will use to integrate forward in time. So let's switch over to MATLAB and start coding this up. All right, here's the command window in my MATLAB. I'm going to go ahead and start by writing a script. I'm going to do this all in a script format. And I personally, when I start my scripts, like to start with clearing my workspace. So I clear all, close all, and CLC. Close all will close any open windows, such as plot windows or figure windows, and CLC gets rid of any commands in the command window. So we said that ODE45 has two outputs. So this would be T out and S out. And the inputs are going to be a function handle towards a function name. So I'm going to call this function for our spring ODE, and I'll have to write that function, and that's what we'll do next. I need a t-span, and I need an initial condition for my state variable vector that I'll call s naught. So this is the bare bones of what we need to run ODE45. Now I haven't defined what s naught is, and I haven't defined what t-span is yet. I haven't even written spring ODE, but we'll do that next. So for our time span, let's say that I want to simulate this spring oscillating for, let's say, 10 seconds. So t-span only needs to be a start time and a final time. So I'm going to do 0, 10. So this tells MATLAB start at time 0, end at time 10. But it does need these initial conditions to start things off. So the initial condition s naught tells us what is our state variable vector to start things off. Going back to our example problem here, let's say that the resting position of this spring is 1 meter. And let's say that I grab onto this mass and pull it to the right to a measurement of 2 meters and let go. Those are going to be my initial conditions. So I want to say that my initial condition in position is 2 meters, and my initial condition in velocity or horizontal speed is 0. So my initial conditions would look like 2, 0. Something important I want to note here is that I've represented this as a column vector. So I've used this semicolon between the two so that it's a column vector, not a row vector. MATLAB insists that the state variable vector is represented as a column vector. So you will always have your initial conditions as column vectors. And as we start building up this spring ODE, you'll see that that also needs to be a column vector. And at the end of all this, let's plot our results. Let's take a look at what the position is with respect to time. You can imagine that if I pull this mass over to the right slightly and let go, this mass would just oscillate back and forth. So I expect this to look like a cosine wave going back and forth. So I'm going to go ahead and plot time, t out, versus position. And as we said earlier, our position would be the first column of this s out. And I'm going to go ahead and label these axes appropriately. So we have time on the x-axis in seconds, and on the y-axis we will have our x position in meters. Okay, so I'm going to go ahead and save this as a spring example script, And now what we need is just to build up this Spring ODE. So we need to describe how do we get from S to S dot for MATLAB. If you look at the ODE45 documentation, this is often done purely as a function handle within line with the script. I personally like to write them as separate functions. As you start dealing with more complex differential equations, it's often messy to write a full function as a single line of code. So I think it's great practice to write these as separate functions. So I'm going to go ahead and start a new function, and I'm going to call this function Spring ODE. And the output to Spring ODE, as we discussed, needs to be S dot. And the input needs to be time and S. Now you can call these variables anything you want. MATLAB just always interprets the first one as time and the second one as the state variable vector. Now I said earlier MATLAB requires that the state variable vector is a column vector. So the first thing that I like to do in my ODE function is to pre-allocate S dot to be a column vector. So I set this up as a 0 vector, and I know that's going to be length 2. So S dot I say is zeros 2, 1. And now I can start saying what are each one of those indices of S dot. So what is the first index of S dot? Going back to our example problem, we established previously that this first index, if we want to represent it in terms of S, well, this first index is X dot, which in our input S is just the second index. So S dot 1 is simply just S2. It's the second index of our S vector. S dot 2, on the other hand, we said is minus k over m times x, which is represented by index 1 of S minus xr. So I'm going to put that here, minus k over m times S1 minus xr. And this here is our ODE function. We have everything we need in here, except for this is still in variable format. So I haven't defined what k, m, and xr are. And let's go ahead and just pick values for that. So let's say that k, our spring constant, is just 1, and that's in units of newtons per meter. Let's say that the mass of this particle is just 1 kilogram. And lastly, let's say that the resting position, xr, is 1 meter. So I'm going to go ahead and save this as Spring ODE, save. And now this code should run. One point I want to make though is make sure that this script and this ODE function are in the same folder, or at least they're in a known path. If they're not in the same folder or a known path and you try to run this, MATLAB will kick back an error saying that Spring ODE doesn't exist. So if I go ahead and run this, there's our plot. You can see that we started at an initial position of 2 with 0 velocity, so it's not moving up or down, it's just released from rest. And it goes ahead and follows this cosine-like wave as it oscillates back and forth. Our amplitudes are the same because we have no friction in the system, and it has a pretty long period. It takes about 6.5 seconds, it looks like, a little over 6 seconds to go through one full oscillation, and that's largely because of these dummy variables I've picked. In our next video, I'll talk a bit about other options that you can use in ODE45. Thank you.